Okay, we're on to lesson 2.5, which is about perpendicular lines. So if we read the definition about perpendicular lines, it says perpendicular lines are two lines that intersect to form right angles. And we know that a right angle is 90 degrees. So two lines that intersect to form 90-degree angles, or two lines that intersect to form right angles. So what we haven't talked about, or I think I briefly mentioned it in class, is all definitions are biconditional. So you can rewrite this definition of perpendicular lines as a biconditional. Well, first let's try to write each conditional statement. So if the original is perpendicular lines are two lines that intersect to form right angles, well, one if-then statement would be if lines are perpendicular, and I'm going to shorten here, and this is the symbol for perpendicular, then they intersect to form right angles. So again, I'm trying to shorten here by putting symbols. Okay, so that's the first conditional statement. It says perpendicular lines are two lines that intersect to form right angles. So I changed that to an if-then statement. If lines are perpendicular, then they intersect to form right angles. So how could I write the converse of that? Because remember, biconditional means the original conditional and its converse are both true. Therefore, you can write it as an if and only if. So I need to find the converse. The converse would say, if two lines intersect to form right angles, then they are perpendicular. Right? So it would be if two lines intersect to form right angles, then they are perpendicular. So now the biconditional is to put these two things together. Two lines are perpendicular if and only if they intersect at right angles. So it goes both directions. So therefore, if two lines intersect at right angles, then they are perpendicular. If it's given that two lines are perpendicular, then you know that they intersect at right angles. That's merely because of the definition. This is going to become important later. So that's just the definition alone. Okay, let's recall one of our constructions. Okay, so it says construct two lines intersecting at a right angle. So the first thing you need to start with is your line segment. So it says think midpoint. So in other words, if we create a midpoint, we're bisecting this segment, and the only way we can bisect the segment is to bisect it at a perpendicular. So we're bisecting it with a perpendicular line. So here's my segment, AB. In order to bisect this segment or construct a perpendicular, I need to make sure my compass is open wider than the halfway mark. So I'm thinking the halfway mark is about here, so I'm opening a little bit wider. And you make that arc, remember this is like the radius of a circle, so it's some distance here. Now we're going to go ahead and imitate that distance on the other side, making an arc here. Then you're going to line up your ruler, which I'm lining mine up. You can't see it, but I have mine up here on the board, so it might be a little off. And here it is, cutting through, and then this is my perpendicular symbol. So I just created a perpendicular bisector. So what does that mean? That means I bisected this. So if I called this A and this B and this C, I made AB congruent, segment AB congruent to segment BC. Not only that, let's call this point D up here. Maybe use a different color, sorry. I made angle DBC equal to 90 degrees. So the measure of angle DBC is equal to 90 degrees. Or I could say angle DBC is a right angle. So construct two lines intersecting at a right angle. I just did that. How did I do that? I constructed the perpendicular bisector, and the perpendicular bisector goes through the midpoint. So in other words, that is the midpoint right there. So B is the midpoint of segment AC. Okay, so it says letter A. What do you know about the three other angles formed by the two intersecting lines if one angle formed is a right angle? Okay, well, we've studied supplementary angles, which said that this is a straight line right here. ABC is a straight line. So therefore, that must be that angle ABC is 180 degrees. It's a straight angle. Therefore, angle ABD must be 90 degrees because it's supplement to DBM. Right? So these are supplementary angles. They must set up to 180. Well, if this is 90, then this also must be 90. And then you have supplementary angles here. This line BD is also a line making a straight angle, so these must be 90, 90. And then same thing here, 90, 90. Same thing here, 90, 90. So what do you know about all the other angles? They're all 90 degrees. How do you know this? Well, I just did that because of the supplementary angle, the straight angle, and their supplementary angles, so we're combining those two things together, right? We know the definition of a straight angle is that this angle ABC is a 180 degree angle, and we know the definition of supplementary angles, so if angle DBC is 90 degrees, then angle DBA has to be 90 degrees because those are supplementary. Or you could do the angle addition postulate. Right, if this is 180, we subtract 90 from it. The angle addition postulate says that angle ABD plus the measure of angle DBC must equal the measure of angle ABC. Okay, the symbol that means perpendicular, well, sorry about that, I already used it above. So this symbol means perpendicular, which is why up here I was using that symbol. State 3 real-world examples where perpendicular lines exist. Oh my gosh, those never end. Hopefully you're just instantly looking all around the room saying, oh yeah, the window frame, the wall meets the floor, the poster corners, everything, you know, the book, your corners of the cover of the book. There's stuff all over the place. Okay, so let's look at this diagram and try to answer these questions. It says if line AB is perpendicular to line CD, use the diagram to classify each statement as true or false. So when I get information like this, I like to mark it in my diagram so my brain can see it as well. So I have line AB right here, I have line CD right here, and so I'm going to mark this as 90 degrees. Now, does it look like it's 90 degrees? No, but you cannot trust what the diagram looks like. You can only trust symbols that are given on the diagram, and you can trust given information and make those symbols on the diagram so you know that is in fact true. Okay, letter A. Is AB perpendicular to EF? Do we know that to be an absolute fact? Well, if AB is perpendicular to CD and EF cuts in between them, then that should be a definite false. Is angle CGB a right angle? CGB a right angle? Well, yes it is. If this one next to it, CGA, is a right angle, these are supplementary or angle addition postulate, so yes, we know that is true. Is angle CGA a right angle? Yes it is. That was the definition of perpendicular lines right here. If those two lines are perpendicular to each other, then we know they intersect at a 90 degree angle or a right angle. Is angle DGB a 90 degree angle? Yes, it is. Again, that's definition of perpendicular lines. If CD is perpendicular to AB, then we know that they intersect at a 90 degree angle. Are EGC, so EGC and EGA complements of each other? Well, I can see here by outlining them, they made the entire 90 degree angle, so yes, they are complements of each other because they add up to 90 degrees. Let me get a different color here, is DGF, so DGF is complementary to DGA. Okay, now look at this one. Is that going to be complementary? No, that's false, because this is beyond the 90 degrees. This is within this 90 degrees. This would be 90 degrees over here on this side. So see this red mark right here? So we have this 90 degrees plus something additional. So no, that's false. These are not complementary to each other. I'm going to erase what we have so far because it's hard to see. So our last one is EGA is complementary to DGF. Oh, okay, that's a little bit tricky. Are those complementary to each other? Yes, actually they are, right? These are vertical angles right here. This was a line. Let me draw those in a different color. This was a line, and this was a line. Therefore, these are congruent vertical angles. So if these two are complements, then these two must also add up to 90 degrees. So yes, that is true. Those are complementary. That's because of the vertical angle theorem added in there. Okay, so far we have the definition of perpendicular lines. The definition says that if two lines intersect if two lines intersect at 90 degrees, and they are perpendicular. Or if two lines are perpendicular, then they must intersect at 90 degrees. So it's either direction. Here, 2.4 is slightly different. It says perpendicular implies congruent theorem. That's the name we gave it, not the name from the book, but it's theorem 2.4 in the book. It says if two lines are perpendicular, then they form congruent adjacent angles. Okay, if two lines are perpendicular, we would have angle 1, 2, 3, and 4. They form congruent adjacent angles. Yes, that's true. The definition says that if two lines are perpendicular to each other, they form a 90-degree angle. And then we went around and we said all four of these would be 90 degrees because of the supplementary or angle addition postulate or supplementary angles. Well, here's a theorem that then says that to us. If two lines are perpendicular, then they form congruent adjacent angles. So all four of these angles are congruent and they're side by side. They share a common side. Notice, it doesn't say they form 90-degree angles. It says they form congruent adjacent angles. Now what do you notice about 2.5? If two lines form congruent adjacent angles, then they are perpendicular. What is the relationship between 2.4 and 2.5? 2.4. If two lines are perpendicular, then they form congruent adjacent angles. 2.5. If two lines form congruent adjacent angles, then they are perpendicular. So what are they? You just took a quiz on this. Hopefully you're saying to yourself, oh yeah, those are converses of each other. They are converses of each other. So it goes both directions here. So this is the converse, and again, if two lines form congruent adjacent angles, then they must be perpendicular. Okay, now our goal for the day is to try to get down here to this table and to distinguish the difference between the definition of perpendicular lines and theorem 2.4 and theorem 2.5, along with other theorems that might come up. Okay, but before we do that, let's look at this example up here. We have one more theorem. It's the split complements theorem. So you're splitting complements, making complements. If the exterior sides of two adjacent acute angles, so if the exterior sides of two adjacent acute angles, so here we go. The exterior sides of two adjacent acute angles are perpendicular. Here's an exterior side, here's an exterior side. Angle 1 and angle 2 are adjacent acute angles, right? They're less than 90 degrees. They share a common side, which means they're adjacent. Their exterior sides, which is the green part, are perpendicular to each other. So this is 90 degrees right here. Then angle 1 and angle 2 must be complementary. Then in other words, the measure of angle 1 plus the measure of angle 2 must equal 90 degrees. That's what that says. So if the exterior sides of two adjacent acute angles are perpendicular, then these two angles must add up to 90 degrees. They must be complementary. So let's put that into perspective. Use the provided diagram to write a mathematical sentence that represents theorem 2.6. So look at what I did here, and you translate it into this diagram. So you should be writing the measure of angle ABD plus the measure of angle DBC equals 90 degrees. That's what that means. Okay, now you might want to take a moment and try example 3 on your own down here. Otherwise, you'll have to watch video number 2, part 2, to go through this, but you might want to try a little bit on your own before you watch the second video. All right, talk to you soon.